Okay, so in this video we will be doing the one of the few last topics of this chapter 5. Okay, the first topic is compound Poisson process. Okay, so as the name suggests, the compound part actually it is the extension of a regular Poisson process. Okay, and the regular Poisson process is signified by a rate lambda which is greater than 0. It means that the events are occurring over time with a regular or constant rate of lambda which is greater than 0. It means that something is happening over time. Okay, like for example, we are entering a store. Okay, so the number of people per minute or per hour entering the store is actually a Poisson process, and it is signified by this lambda. The arrival rate is lambda. Okay, and it is greater than 0. Some people are entering the store every hour or every minute or every half hour and so on. You can keep the time frame from minute to hours to days, that doesn't matter. Okay, so in a regular Poisson process there are some events. Okay, and the total number of events are xt. Okay, x number of events occurring over time. Okay, we have, and it is equal to n. There are n number of events occurring over the complete time frame. Okay, so these are the two aspects of the regular Poisson process. So in the compound Poisson process, it is the extension of this regular Poisson process. Okay, and this compound, this is the accumulative or summative, okay, the sum of impacts of these events occurring over time with the rate lambda greater than 0. Okay, so it is the extension of this regular Poisson process. But in this compound Poisson process, what we do is we accumulate the impact of these total events occurring over time. Okay, so like in practical terms, I must take it in practical way. Okay, then you will understand. So in practical terms, actually this compound Poisson process or CPP, actually it models situations where each event xi of t, okay, this is a random event, okay, results in shock, or we can say it result in change. Okay, so we want to measure the total change over time. Okay, I will explain it using some graph. Okay, I hope you have understood this practical thing. It means that we have a time frame. Okay, this is the time frame. Okay, this is the time t, and this is the waiting time w. Okay, so for each event to occur, actually the system had to wait for the time. For example, for the first event to occur, w1 is the time that the system actually waits. Okay, and here we have another random variable which is y1, which is the event that has occurred after w1 time. After waiting for w1 time, y1 is the event that has occurred. Okay, and similarly after some time, okay, w2, there is another event that has occurred, which is y2. Okay, now this event, actually y1 occurring over this time, it brings some change into the system. Okay, for example, we are in a store. Okay, so this is the first customer that has arrived into the store. Okay, so now the dynamics of the store has changed. Okay, now we have one customer in the store. Now after some time, we have another customer in the store, so event 2 has occurred. Now it has further changed the system. Okay, similarly y3 and y4 and so on, so it will make, a graph like this. Okay, like after every wi an event is occurring. Okay, and y1, y2, y3, these are the identical random variable, identical distributed random variables. Okay, that are the events occurring over the time period t. Now to measure the impact of these events occurring over time cumulatively, what we do is we call it the compound Poisson process. For example, the insurance claiming model. Okay, the insurance claim model. Okay, you must have experience with insurance. Some people insure their cars, insure themselves, for some health medical reasons. They get some hefty amount, on being sick, or when they have some disease, or when their car is damaged in some floods or in some accident. The insurance company actually pay them a hefty amount after some time. Okay, so this is this model is the insurance risk model. Okay, so in insurance risk model, I must explain this thing using this insurance risk model. You will understand it over here. Okay, so there are claims. Okay, every customer actually make claims, that arrive at insurance company. Okay, over time period t, and it follows a Poisson process. Okay, now the amount, this thing, like we discussed over here, the event occurring over here, the impact of this event is y1, which is identically distributed random variable. So the amount of claim is yi. Okay, this is the random variable y. Okay, the amount of claim that is occurring, at each time, this is actually yi. Okay, now if you want to calculate the cumulative claims that the insurance company gets over time, then we use the compound Poisson process. Okay, so with each claim coming, there is some impact that is happening on the company. They are debiting some amount. Okay, so if we calculate collectively the amount of debits that the company is paying over time, or the amount of claims that are happening over time, this is called the compound Poisson process. This follows the compound Poisson process, and it can be mathematically annotated as z of t is equal to summation of y k's or yi's for k is equal to 1 up to x of t, where x of t is the total number of events that is happening. We can also take it as equal to n. Okay, so from first claim k is equal to 1 up to the nth claim or the kth claim, we have to make the summation of those random variables. Okay, and this will give us the total impact. Okay, so this is the compound Poisson process. Okay, now in the next video I will be doing the other mathematical parts, the risk models or the shock models, their mathematical representation, explanation and all that, and also the fewer examples. Another example is that you are entering stock market. Okay, and you buy some stock. For example, you buy stocks of an oil company, for example, Kuwait oil company. Okay, now it will begin at some time t is equal to 0. Okay, for example, in January you bought some stocks. Okay, so so the January is actually your initial time, t is equal to 0. So actually the stocks, they are analyzed daily, but for the sake of understanding the system, actually we will do it like weekly. Okay, so after 1 week time, W1, actually your stock, actually the stock price goes upward. Okay, so this is the first change that you get, Y1. Okay, now after the second week, W2, actually your stock prices improves further. Okay, but at the third time, W3, actually the stock prices, it plummets or it's plunged down. Okay, and in the fourth it recovers a little bit. Okay, and so on. You analyze it over the week and you find like a wave shape kind of output. Okay, now to analyze the cumulative impact of these changes, whether you are gaining or you are you are losing, we use the compound Poisson process, CPP. Okay, and this CPP can be denoted by Z of t, which is Z of t is the overall impact. Okay, or the cumulative impact, and it is equal to summation k is equal to 1 up to n or x of t, number of events, y k. Okay, I hope you have understood the the compound Poisson process. Okay, so in this one, this ykk is the identically distributed, independent and identically distributed id random variable. Okay, and it is the size of the kth increment or decrement. Okay, and x of t is equal to number of events, okay, distributed over time t. Okay, and these number of events follows the Poisson distribution. Okay, and its rate is lambda. Okay, I am writing t over here because we know that if the single time the rate is lambda, so over the time period t, its rate will be lambda into t. Okay, so this is how the compound Poisson process can be mathematically written. Now we have some properties of the compound Poisson process. Okay, we have some properties, and in those properties we first have the expected value. Okay, and the second one is the variance. Okay, so the expected value of this z of t, okay, the CPP, which is denoted by z of t, it is equal to the expected value of summation of yk for k is equal to 1 up to x of t. Okay, so it will be equal to expected value of this x of t, okay, multiplied by the expected value of the shocks, okay, and it will give us the expected value of xt is lambda t, as we previously did it. Okay, so lambda t multiplied by the expected value of y is the mean change, okay, which is mu. So lambda mu t or lambda t mu is actually the expected value of this compound Poisson process. So in a question, if you want to find the expected value, okay, of certain compound Poisson process, we will use the formula lambda t into mu to calculate it. Okay, E of y, it is the expected value of the single shock, and expected value of single shock can be found by leveling or aggregating or averaging all the shocks, okay, so which is represented by mu. Okay, now the second property is the variance. Okay, so variance of z of t is equal to expected value of variance of zt such that we have total number of events x of t, okay, plus variance of expected value of z of t such that we have total number of events of x of t. Okay, this is the law of total variance. Okay, so as we know that x of t is Poisson distributed, okay, we have a rate of lambda t over here, so the variance of z of t is equal to expected value of x of t into variance of y plus variance of x of t and e of y whole square. So it will give us lambda t sigma square plus lambda t mu square plus so if we have lambda and t as common, so taking lambda and t common, we get sigma square plus mu square. This is the variance of z of t compound Poisson process. Okay, and sigma square is the variance of y. Okay, variance of y. And what is y? Y is the single shock or single change. Okay, these are the two properties of the compound Poisson process. Okay, so in the previous video we talked about the two properties of the compound Poisson process CPP. Okay, the first property is the expected value, okay, E of z of t, which is equal to lambda t into mu, and the second one was the variance of the z of t, and it is equal to lambda t into sigma square plus mu square. Okay, so you only have to memorize these two equations. Okay, so that if there is any question and we want to find the expected value of the net change z of t, so we can use this formula lambda tu, and similarly for the variance we can use the lambda t into sigma square plus mu square formula to calculate that. Okay, now we come to the distribution of CPP or compound Poisson process. Okay, so we know that y1, y2 up to yn are independent and identically distributed random variables. Okay, we call it IID. Okay, now the sum of these, actually the distribution of the sum of these will be the convolution, actually the convolution of the each independent random variable. Okay, so we will use the convolution notation to calculate that. Okay, and convolution, basically we will use convolution. Okay, convolution. And what is convolution? Convolution is basically a method to find the distribution of sum of independent IIDs, random variables. Okay, if we have identically distributed random variable, so the convolution method is used to find the distribution of the sum of these random variables. Okay, so to find the distribution, okay, the distribution of the sum of these identically distributed and independent random variables, what we do is we use the convolution method. Okay, and why we use this? Because the CPP is actually z of t, and it is equal to summation of k is equal to 1 up to x of t y of k. Okay, so it is the summation of these random independent random variables. Okay, so whenever there is a summation, we use the convolution method to find the distribution of this sum. We know about the distribution of this independent single one. Okay, for example y1, we know about the distribution of it, but what will be the distribution of the sum of all these, that we need to find using the convolution method. Okay, so z of t actually such that the total number of events occurring is equal to n is equal to y1 plus y2 plus y3 plus y4 plus yn up to yn. Okay, I wrote it over here, so it is the simpler form of it. Okay, expanding it we will get this thing. Okay, now we want to find the g of n, actually when we have the y number of events. Okay, and it is equal to the probability that the summation of these independent random variables up to n, okay, it is less than or equal to this y. Okay, and if you want to find the probability of this, it is going to be equal to this thing. We will use the integration method to find the probability. Okay, so the probability that z of t is less than or equal to small z is equal to the probability that the summation of these independent random variables for k is equal to 1 up to number of events n of x of t, okay, it is less than or equal to z, because this summation is represented by z of t. Okay, so both are interchangeably, it can be written. Okay, so when we open this thing, okay, we found it equal to summation of n is equal to 0 up to infinity into the probability of summation of yk for k is equal to 1 up to n number of events, okay, less than or equal to z, such that the total number of events is equal to n multiplied by lambda t raised to power n e raised to power minus lambda t divided by n factorial, and this is actually equal to the probability that number of event is equal to n. It is equal to lambda t raised to power n e raised to power minus lambda t divided by n factorial, which is the Poisson distribution. Okay, so the total number of events, actually it follows the Poisson distribution, but the summation of it actually is the multiplication of such that the collective events yk is less than or equal to z, such that total events occurring is equal to n into probability that total event is equal to n. So we know the probability x3 is equal to n is this thing, so and this is equal to this thing, gn of z multiplied by lambda t is power n e is power minus lambda t divided by n factorial, and this is equal to the probability that z of t is less than or equal to z. Okay, so just like we write that probability that x of 1, okay, is less than or equal to 2 or something like that, we use some formulas. Okay, so this is the for total number of events z of t, the net change. Okay, this is for independent one event, and this is for the collective events. Okay, for example, you want to find probability that the net stock reduction or stock improvement is less than, for example, $5. Okay, so we will use this formula. Okay, so this is the distribution of the summation. Now I will explain the shock model and all, and then we will come towards the solving few example. When we solve few example on it, you will, it will be helpful in understanding the whole process. Okay, let me know if there is any confusion. Thank you. Okay, so some explanation regarding the convolution method and the sum of it. Okay, so z of t such that the total number of jumps is equal to n is equal to y1 plus y2 up to yn, because we are investigating it for the n jumps. Okay, so probability that z of t is less than or equal to z is equal to the probability that total number of events or jumps are occurring is equal to n multiplied by gn of z. Okay, and gn of z, this is for n jumps, okay, is equal to the cumulative distribution of sum of n number of jumps. Okay, this is the cumulative distribution Gn of z. Okay, and this Gn of z actually it is equal to probability that the sum of these events, independent events up to n, is less than or equal to z. Okay, this is a cumulative distribution. Okay, and it is found using the integral. It is equal to integral from minus infinity to infinity g for n minus 1 y minus z differential with respect to g of z. Okay, this is the n cumulative distribution for this n jumps. Okay, so this thing actually probability that the total is less than z, okay, is equal to probability that summation of yk for k is equal to 1 up to total n, okay, number of events yk is less than z such that total number of events is equal to n multiplied by the probability that the total number of events is equal to n. Okay, so we know that the total probability that we have n events over the time period t, it follows Poisson distribution and is equal to e raised power minus lambda t raised power n divided by n factorial. So putting the value, we get the probability that the net change is less than or equal to z is equal to this thing is equal to this Gn of z, okay, is equal to Gn of z multiplied by e raised to power minus lambda t raised to power n divided by n factorial. So this is the equation that we got earlier. Okay, this was just to remove any confusion like how we get it. Okay, this is just an explanation. Now I will do the shock model and I will explain that, and then after that I will be doing the examples based on this shock model and investment models. Thank you. In this video we will be doing the shock model. Okay, what this shock model actually shows us, or what does it mean, so we will know in this video. Okay, so we know that we have x of t is equal to n, and it shows the number of shocks or events over time. Okay, this is the basic property of a Poisson process. Okay, so the shock model actually comes under the CPP, which is a compound Poisson process, and it deals with the compound or collective effect or shocks in time duration t. Okay, so the time duration t, for this time t, for example 5 minutes or 10 minutes, the total number of shocks, okay, for example after W1 waiting time 1 we receive the first shock. Okay, this is the first shock. Then after some time we receive the second shock. This is the W2, which is the waiting time for the second shock. Okay, then the third shock. Okay, then the fourth shock, and so on. Okay, and the shock is random. Okay, here it is increasing up to W3, but here it is decreasing, so it will be like a staircase form. It will be random. It will increase sometime, it will decrease sometime. For example, let this shock be the stock price in the market. Okay, so here the stock price is increasing over here, okay, up to W3, but up to W4 we have a decrease, a drop in the stock prices. Similarly, this can be done as the crack generation. Okay, here we have a crack, here the second crack, this is a large crack, third crack, okay, and so on. So this shock model actually can be used in the banking, the stock markets, the cracks generation, and any field, okay, which have the description of the events happening in this way. Okay, this is the time period T in this direction, and this is the intensity of the shock. So what we do in this shock model, we calculate the collective shocks Gn of A, which is the probability of that the collective shock is less than A. A is the intensity of this shocks. Okay, when these shocks happen actually, okay, the intensity is increased, okay, because it is in incremental form. Okay, here we receive some shock, and these shocks will add and it will disturb the system. Okay, so it will add up till the intensity A, because after A, okay, when we collect such shocks up till A, the system will break then. For example, we have a bridge. Okay, so in the bridge we have some, for example, we have load on it. Okay, so the load that is happening, we identify it as a shock. Okay, so for example, we have a bridge. Okay, this is the bridge that is crossed by a number of vehicles. Okay, for example, we have only one vehicle at a time. Okay, so the depression in it, okay, it will be lower. So this is the first shock to the bridge. For example, a second, this moves forward, okay, and a second one also enters. Now we have two vehicles. Now the collective shock actually, it will deepen. Okay, it will be more, and it will increase up till the level A. Okay, A is the intensity of this shock. For example, we have like 12 vehicles we have a congestion over here. Okay, and there are 12 vehicles, long vehicles, moving on the bridge. Now up till A, the bridge can actually it can bear the load, but after A, the bridge will break. So A is the intensity level up till which the system can actually absorb these shocks or failures, but after that the system will collapse. Okay, so Gn of A is the collective probability that the collective shock is less than A, where A is the threshold level, okay, for which the bridge or the system is still working. But after A, if the collective shocks is greater than A, then the system, then further on, it cannot absorb more shocks. Okay, so this is the overall details of the shock model. So let's xt be the number of shocks that a system have up till time t. Okay, and y k is the damage, okay, or wear, okay, incurred by kth shock. Okay, because the shocks are happening in a sequence, so yk is the damage or wear incurred by the kth shock. Okay, while k is equal to 1, 2, 3 up to n or anything. Okay, So this is the sequence of the damages that is happening. Okay, and these damages actually sums up, okay, y1 plus y2 plus y3. Okay, the shocks will sum up to bear a load on the system. Okay, so we assume that the damage is positive, it is not negative. Okay, it is only like this. Okay, it is positive. By positive we mean that the probability that yk is greater than 0 is equal to 1. It means that there is at least some damage that is happening with every shock. Okay, there is no shock that is not making any damage or anywhere in the system. So we assume that the damage is always positive. Okay, the next assumption is that we have the summation of these yks for k is equal to 1 up to n, or x of t is equal to n. Okay, it is equal to z of t. It means that the damages actually accumulates. Damages accumulates additively or positively. Okay, the damages that is incurred with each shock actually it sums up. Okay, and that sum is identified by or represented by z of t. Z of t is the collective damage that has been done with these independent and identically distributed damages or wears due to the shocks. Okay, now suppose that the system continues to operate as long as this damage is less than some critical value a. Okay, we have a value a which is this summation of the damages. Okay, and up till this, actually up till this the system sustains. Up to this level system sustains, but after this the system fails. So this a is the threshold or the critical level of this collective damage, this yk, summation of yk's. Okay, now let's capital T, okay, represent the time that the system fails. Okay, capital T is the time that the system fails. Now when is the system failing? The system is failing after this a, small a, which is the critical level. Okay, and this is the summation of these damages. Okay, and this summation of these damages is represented by z of t. So capital T is the time that system fails, and z of t is the collective damage. Okay, now if t is greater than t, okay, then this z of t is less than a. Okay, if the time of failure is greater than a time period, it means that the system never fails. Then the collective damage is less than a. Okay, if this time t is less than the time period t, which is the total time of the system, okay, then it means that the system has failed at some point, and that is then the z of t will be greater than a. The collective damage must be greater than a in order for the system to fail. Okay, so remember this, that for t greater than t, small t, okay, then z of t, the collective damage, is must be less than a, the critical level. If it is greater than a, it means that the system has failed. Then the capital T is less than the overall time period. Okay, I will explain it in the next video. Okay, I hope you have understood that if the total damage Z of t is less than A, then capital T, which is the time of failure, okay, it is greater than the total over time. It means that it will take some more time, okay, to fail, okay, and this level A, it will be soon equal to Z of t, okay. Like for example, it is the point A, okay, this is the critical level. After this the system will fail, okay. Okay, and suppose we want to investigate it for this time period capital T. This is the time period capital T, okay. Sorry, small t. This is the small t, okay. Now this is small t, okay. This is the time period for which we want to investigate. For example, 2 hours, we are getting 2 hours time, okay. Now when the shocks are happening, okay, it will make a graph like this, okay, somewhat like this, okay, and it will receive shocks at some points over here, okay. Now these shocks will be collecting at this point, and it is Z of t. For example, here the magnitude of the shock is, for example, 1.5. Here it is 2.5. So up till now we have Z of t is equal to 4, okay, and here we have 3.5. Here the collective is 7.5, and so on. So the Z of t, this collective, okay, and this is the critical level A. Now with this collective Z of t, the collective damage, when it reaches the point A, the system will break, okay. But before A, the system is maintaining itself, it is not breaking, okay. So if you want to investigate it for like a certain time period, or the failure time, here at this point the time period is equal to capital T, okay, and we are investigating it for up to this time period. This is small t, 2 hours, okay. Now 2 hours, this small t, it is less than capital T in this case, because capital T is somewhat over here, and it is like, for example, 3.5 hours, okay, but we are investigating it for the 2 hours time, okay. So small t, it is less than the capital T. It means that the system has not reached yet the critical limit A, okay. So the system will not break at this point, and vice versa. If the system reaches at this point, it means that this capital T, actually, it is now less than the total overall time, okay. For example, we are investigating it for this much time, for example 4 hours, okay. So then the capital T is equal to 3.5 hours, which is greater than which is less than the 4 hours, which is small t. So when this time T, capital T, which we know that it is the time that when the system fails, okay, the expected time when the system fails, it is less than the total time period. It means that the system has broken down earlier, okay, or the Z of t is equal is the Z of t, the overall damage, it is greater than this critical level A. It exceeds at this point, for example, here at this point, this is A, and this is Z of t. So Z of t has exceeded the A, it is greater than A. So for this we have this capital T small than small t, which is the overall time period. I hope you have got my point, okay. Let me reiterate it for once so you understand it. Okay, we have 2 points. Okay, for example, this is small t. Okay, this is the time, expected time in which the system fails, and this is the critical limit a. Okay, so when the shocks are happening, it will reach ultimately at this point. Okay, which is z of t. This graph is z of t. This is the collective damage that has been done at each shock. Okay, we are adding these shocks. Okay, which makes capital Z of t. Okay, so when z of t is less than a, the system will not fail, and for that the capital T will always be greater than small t. Okay, and vice versa, when the capital Z of t, okay, it is greater than a, it means that we are somewhere at point here. Earlier we were behind the a, now we are, somewhat in front of a. Okay, we have crossed this a, we are now at here, some point over here. Okay, now for this it means that the collective damage has exceeded the critical level, and for that the capital T is always less than the small t overall time period. It means the system has failed prematurely before we end the expected time to, the expected time for a system to fail. Okay, we will find the equation for this thing. Okay, we know that probability that the overall damage, collective damage, is less than some level z, it is equal to the probability that the summation of yk, we know that the summation of yk is equal to capital Z of t, for k is equal to 1 up to the total number of events, it is less than or equal to small z, this level. Okay, we will then convert the z into a. Okay, this is the critical level. Okay, we have this equation. Okay, and for that this is equivalent to the probability that capital Z is less than or equal to small z, which is a critical level. It is equivalent to the probability that we have the total number of events is equal to n multiplied by the probability that yk summation is less than or equal to z, such that the total number of events is equal to n. So we have one conditional and other is the probability that total number of events is equal to n. Now this is a Poisson process. Okay, so this is a Poisson distribution, and we know that the probability that x of t is equal to n is equal to e raised to power minus lambda t raised to power n divided by n factorial. Okay, we know this thing. Okay, now we need to know the probability, the other factor, which is probability that summation of yks is less than or equal to z, such that x of t is equal to n. Now this thing is equal to g n of z, which is the probability that total or collective damage or shock is less than or equal to z. Okay, this is the probability. So putting these values, we get the probability of z of t less than or equal to z is equal to g n of z into e raised to power minus lambda t raised to power n divided by n factorial. Okay, now we have one part of it. Now another one is t is greater than small t if and only if this z of t is less than the critical level of A. We know that. Okay. Now we will use both of these to find the expected time of the system failure. So the capital E expected value of this time period t at which the system fails is equal to the integral of probability that this capital T is greater than small t dt. Okay, it is equal to this thing. Now probability that capital T is greater than t is only when the z of t is less than or equal to A. Okay, and we know that t is greater than t for only when the z of t is less than or equal greater than or equal to the critical level A. Okay, and when is z of t greater than or equal to A? Okay, it is when this thing happens. The probability that z of t, the overall damage, is greater than or equal to the z level. Okay, so expected value of t is equal to summation of n is equal to 0 up to infinity into the integral of lambda t raised to the power n and e raised to the power minus lambda t divided by n factorial multiplied by dt multiplied by g n of A. Okay, so when we integrate it, actually we get 1 over lambda into summation of n is equal to 0 up to infinity gn of A. This is the expected value that the system will fail. It shows us the time period, the expected time period at which the system will fail. This is the equation. Okay, now I will further generalize it for the exponential distribution. Okay, we find out that the expected time of failure E of t is equal to 1 over lambda into summation of n is equal to 0 up to infinity g n of A. Okay, where A is the critical level. Okay, and n is the shock level. Okay, and we know that g0 of A is equal to 1. The probability that the the collective damage is 0 is equal to 1 when there is no shock absorbed. Okay, so when there is no shock, the collective damage is 0, so the probability is 1. Okay, when there is no shock, then the probability is equal to 1. So the ET is equal to 1 over lambda into summation of Gn of A. Now here we have a special case when the individual damages y1, y2, y3 up to yk are exponentially distributed. The individual distribution of these shocks are exponential. The exponential, by exponential I mean that it is either like in this condition or it is either in this condition. This is negative exponential, this is positive exponential. Positive and negative. Okay, it will drop from certain level, rigorously Okay, it will make a steep slope, and same is the case when it is positive, it will climb like exponentially. Okay, all of the sudden it will climb and show a very high pace while climbing. So it is positive exponential, this is negative exponential. Now when these individual damages or shocks are exponentially distributed, then the expected time for the system to fail is equal to 1 over lambda into one plus mu a, or 1 plus mu a divided by lambda. Both are okay. Okay, this is the special case, and it is applicable only when we have y1, y2, y3 up to yk when they are exponentially distributed. Okay, these equations are very important, this equation and this equation. Okay, and I hope that there is a 90% chance that we get a question on this in exam. Okay, on the shock model. Okay, because exercise also have majority of questions based on the shock models. So this was all about the shock models. Okay, now I will do some problems on this shock model, and then after that I will go towards the Poisson marked Poisson process. Okay, so in this video we will be doing the exercise problem. This is the exercise 6.2, and it is based on the compound Poisson process, CPP. So let's write the statement for the question. Okay, the statement is that shocks occur to a system according to Poisson process of intensity lambda. Okay, each shock causes some damage to the system, and these damages accumulate. Let's n of t is the number of shocks up to time t, and yi be the damage caused by the ith shock. Then x of t is equal to y1 up to yn. Okay, this is the total damage up to time t. So they want us to find the mean and variance for the total damage at time t. Okay, and it says that the individual damages shocks, they are exponentially distributed with the parameter theta. Okay, so let's find out the mean and variance for the total damage. Okay, so here there are 3 or 4 things that are given to us. The first thing that is given to us is that the shocks actually they follow a Poisson process with intensity of lambda. Okay, the second thing that is given to us is that each shock gives some damage to the system, and these damages accumulate, and n of t, this is the number of shocks, collective shocks up to time t. Okay, n of t is the number of collective shocks. Okay, the third thing that are given is that each shock is exponentially distributed. Okay, okay, and the parameter, the fourth thing is that the parameter is theta. Okay, these 4 things are given to us. Okay, now we find the expected value of this number of collective shocks up to time t. Sorry, this is z of t, this is z of t. Okay, because n of t is the total number of shocks, and z of t is the damage, that is, which is the summation of the yk for k is equal to 1 up to n of t. Okay, so E of Z of t is to be found, and the other thing is the variance of this Z of t, the total overall damage. Okay, now we are given that each shock is exponential distributed. It means that the expected value of actually yi is 1 over theta. Okay, the expected value of exponential distribution is 1 over the parameter. Okay, here parameter is theta, and the variance of each individual shock, this is 1 over theta square. Okay, because in exponential distribution we have the variance of that random variable is 1 over the parameter square. Parameter over here is theta, so 1 over theta square. Okay, these two things you must know. Okay, and these are given in the table, the handouts. Okay, the teacher will give you handouts, and these things will be mentioned over here for each distribution, maybe. Okay, if not, you have to memorize this. Okay, so these things are given to us. Now Z of t for any process in which the damages is accumulated with each shock is equal to the summation of yk for k is equal to 1 up to n of t, because here we have n of t, we are not using x of t because we have n of t given is the number of collective shocks up to time t. Okay, so this is the, we can also use yi. Okay, that doesn't, we can also use it as summation of yi for I is equal to 1 up to n of t. Okay, so both are okay, both are same. So now the expected value of this Z of t is equal to the expected value of summation for I is equal to 1 up to n of t y of I, while yi is the individual damage that is done with each shock. Okay, now we have a condition that the total number of shocks is equal to n of t is equal to n. So conditioning this expected value, conditioning expected value with n of t is equal to n, the total number of shocks is equal to n. Okay, so the expected value of Z of t such that the total number of shocks is equal to n, it is equal to summation of I is equal to 1 up to n of t expected value of yi. Okay, now the total number, because these are identically distributed, we have it is equal to n because the sum is n. Okay, into expected value of summation of I is equal to 1 up to n of t expected value of yi. Okay, now the total number, because these are identically distributed, we have it is equal to n because the sum is n. Okay, into expected value of y. Okay, because all y's are identically distributed. Okay, so n into e of y for exponential distribution is 1 over theta. So n into 1 over theta is equal to n by theta. This is the expected value of Z of t conditioned on such that the number of total collective shocks is equal to n for time period t. Okay, now applying the law of total expectation. So the expected value of Z of t is equal to the expected value of Z of t such that n of t is equal to n. Okay, so here we have expected value of n of t into the expected value of z of t is 1 over theta. We already found it. Okay, so it is equal to 1 over theta is constant, so it will get outside, and expected value of n of t. Okay, and n of t is Poisson distributed with the parameter lambda t. Okay, so it is equal to 1 over theta multiplied by lambda t, okay, or lambda t divided by theta, and this is the expected value of this z of t. Now we need to find the variance of this z of t. Okay, so for that we need to find the variance using the law of total variance. Okay, and the law of total variance says that the variance of z of t is equal to the expected value of variance of z of t such that n of t is equal to n, okay, plus variance of expected value of z of t such that n of t is equal to n. Okay, expected value of variance of z of t such that n of t plus variance of the expected value of z of t such that n of t is the total number of events or shocks. Okay, so the variance of z of t is equal to n of t is equal to n. Okay, this is already known to us. Okay, the other thing is that we need to find it separately. Okay, first the expected value and the other this the variance of this. So let's find out this one, this one first, or even this one first, whatever we want to. Let's find the second part first, and we will come to the first part then. Okay, so the variance of the expected value of z of t such that n of t is equal to n is equal to, because we have this already in the first part, so that is why I did the second part first. Okay, so the variance of the expected value of this z of t such that number of total events is equal to n, this will be equal to variance of total number of events n of t, okay, multiplied by the expected value of z of t is 1 over theta. Okay, okay, so it will be equal to n of t, okay, multiplied by the variance of 1 over theta. Now the variance of 1 over theta is equal to 1 over theta square. Okay, and that is given to us when we are dealing with the exponential distribution. Okay, this is the thing, variance of yi is equal to 1 over theta square, because theta is a parameter, and n of t, this is the Poisson distribution with the parameter lambda t. Okay, so lambda t multiplied by 1 over theta square is equal to lambda t by theta square, and this is the value of the variance of expected value of z of t such that n of t, the total number of events. Okay, now the second part is found to us, which is lambda t divided by theta square. Now we need to deal with the first part. The first part is that expected value of the variance of z of t such that n of t. This is to be found. Okay, I will continue it in the next video because it is getting long. Okay, so continuing the problem, the expected value for the variance of z of t such that n of t, we need to find this. Now taking the inner portion of it, the variance of z of t such that n of t is equal to variance of summation, because z of t, the summation is yi for I is equal to 1 up to n of t. Okay, now we know that these yi's, the damages incurred by each shock, these are independent and identically distributed random variables. Okay, so all are same actually, so it will be equal to n into variance of y. Now we know that these y's are exponentially distributed, so the variance of y is equal to 1 over theta square, because y's are exponential distribution, so it is equal to n into 1 over theta square. Okay, now we know this is the value for this, the inner thing. Now we want to find the expected value of this. Okay, so the expected value of variance of z of t such that n of t, it is equal to the expected value of n of t multiplied by 1 over theta square. 1 over theta square is constant, so 1 over theta square will come outside and we will find the expected value of n of t. Now n of t, actually it follows the Poisson distribution lambda t, so putting lambda t instead of this thing, so the expected value of variance of z of t such that n of t is equal to lambda t into 1 over theta square, which is equal to lambda t divided by theta square. Now we have the first portion as the second portion, so the variance of z of t, it will be equal to lambda t divided by theta square. This is the first part, plus the second part value is lambda t by theta square, lambda t divided by theta square. So both have common basis, so we can write it as 2 into lambda t divided by theta square. This is the required result. So this is how we find the expected value and variance of this total damage z of t.